Okay, so suppose we have a random variable that has a binomial distribution with parameters n and p. So that is, it's like the sum of the labels on little n draws with replacement from that 0, 1 box. Okay, so what's the expected value? It would be the sum of the possible values times the probabilities of those values. What are the possible values? When we draw n times and add the results on the tickets, little n times, what are the possible values we can see from the sum? We might get a ticket labeled 0 every time, right? Or we might get a ticket labeled 1 every time. The possible values range from there's 0, 1, 2, 3, etc., on up to n. Those are the possible values for the sum of the n draws. So let's say this is the sum from j equals 0 to n. J is now standing for the possible values, okay, of j. That is the possible value. That's taking the role of x of something, right? So it might be 0. What's the probability that it's 0? Right? This is the binomial distribution. So we have j is the possible value, and then this is the probability that we get j successes, that we get j tickets labeled 1 when we draw from the box. We have to get one of the tickets labeled 1 j times. Each time there's probability p that happens. They're independent. So we multiply, and we also have to get a ticket labeled 0 n minus j times. And there are n choose j different ways we can do that in the n trials. Right? This should ring a bell by now, this piece. Okay? So we could do this sum, and it would take us the rest of the lecture. Okay? Or we could use the fact that a binomial is, what has a binomial distribution? Well, little n draws with replacement from that box of tickets. If you take the sum of the draws, sum of little n draws, okay. And what do we know about the expected value of the sum of n draws with or without replacement from a box of numbered tickets? We know that it's little n times the average of the values on the tickets. Yes? And we know that the average on the values of the tickets in this case is p. So this whole thing is just going to be equal to n times p, if we work it out. Yes?
J in front of the binomial distribution is the value on the ticket, right?
Right, so that j is like taking this roll. So this is like 0 times the probability that you get 0, 1 times the probability you get 1, 2 times the probability you get 2, on up to n times the probability that you get n tickets labeled 1. Where did, sorry? Why what? Why did it disappear? Well, we're summing over it. All of its possible values. This is a dummy variable that's just inside the sum. We have, this sum has n plus 1 terms. One of those terms, j, is 0. We get 0 times something. That's not going to contribute anything. Another term, this is 1. So we'll get 1 times n choose 1, which is n, times p to the 1 times 1 minus p to the n minus 1. That's the next term. Then j is going to be 2. We'll get 2 times n choose 2, et cetera. Right? We sum all that up. If we did that, the answer would be n times p. Okay? So using our notion that the expected value of the sum of n draws from a box of numbered tickets is just n times the average of the numbers on the tickets in the box, we can shortcut a very difficult calculation and just write down the answer. Okay? So far, so good? Question? The average of the numbers on the tickets in the box is little p. we're drawing little n times from the box because we're asking about a binomial distribution that has parameters n and p. So it's like the sum of the tickets we get on little n draws from a box where there's a fraction little p of tickets labeled 1 in the box and the rest are labeled 0.